Imagine we had a mixture of gases. Okay, so we have a container here. We just got a bunch of gases in it. So we got this blue gas. We got this green gas. We got this black gas. All right, so 3 gases in there. And we know the pressure that each gas exhibits on the container. But we're wondering, what is the total pressure exerted on the container? That is what Dalton's law of partial pressures is. Dalton's law of partial pressures states that when you have a mixture of gases, the total pressure exerted by all the gases in that container is equivalent to the partial pressure of each individual gas. So if you wanted to calculate the total pressure of all the gases in this specific container, we take the pressure of just the green gas plus the pressure of just the blue gas plus the pressure of just the black gas, and when you add those pressures together, we get the pressure of all the gases in the container. Okay? So an example here, if we're given that we have a mixture of gases, specifically helium, hydrogen, and nitrogen dioxide, and we wanted to calculate what the total pressure of all the gases is, the total pressure exerted by this mixture of gases, we just add up the pressures. So 3 plus 2 plus 5, the total pressure of all the gases within that space is 10 atmospheres. Okay. So that's the first part of Dalton's law of partial pressures. The second part says that if you want to find the pressure of an individual gas in the container, then we look at what is called the mole fraction. The mole fraction for anything is the moles of whatever that specific gas you're looking at. So let's say we have a mixture of A, B, C, right? So you're going to find the number of moles of A and divide it by the number of moles of A plus B plus C. So it's kind of like a percent. Okay? So to find the pressure of just the individual gas in the container, one gas, you take the mole fraction of that gas. Mole fraction looks like this, and you multiply it by the total pressure of all the gases in the container. Okay? That might be confusing, so let's go ahead and look at a specific problem on this side and actually do an example, okay? So you have a mixture of gases which contains 4 moles of oxygen, 3 moles of sulfur trioxide, and 4 moles of helium. And we want to know what the total pressure is. We have the total pressure, sorry, exhibited by the gases, and it's 20 atmospheres. So let me just draw a little diagram for you to understand what I'm talking about. Actually, let me go ahead and do it on this side, because the shadow is going to fall. You're not going to be able to see it. So there's a little container here. And then we have 4 moles of O2. So let me draw this a little bit bigger. Okay. 4 moles of O2, so I'm just going to draw 4 little molecules of O2. Of course, it says 4 moles, but for demonstration purposes, I'm just going to draw 4 molecules of O2. Okay. I'm sorry. That is not O2. Let's just call this H2O. I was thinking something different. Let's just say H2O. Okay, so 4 moles of H2O. It doesn't really make a difference in the math. Okay, so 4 moles of water. Okay, 3 moles of sulfur trioxide. I'm going to draw that with the blue. Okay, so 3 moles of the sulfur trioxide and 4 moles of helium. 1, 2, 3, 4. All right. We know the total pressure exerted by the whole combination of these gases is 20 atmospheres. So total pressure, okay? And we want to find the pressure exhibited by each individual gas, and that's called the partial pressure. So what we have to do is get the mole fraction. So Mole fraction is the number of moles of what we're looking for over the total moles of all the gases. So the mole fraction for water is going to be 4 divided by the total moles of gas, which is going to be 4 plus 3 plus 4, and that is 11. Okay. And then this is the mole fraction for water. Okay. The mole fraction for sulfur trioxide is going to be 3, because there's 3 moles of sulfur trioxide divided by the total moles of gas, which is also 11. I cannot draw this X. It's so bad. Okay, and then the mole fraction for helium is going to be the moles of helium, 4, divided by the total moles of gas, which is 11. Okay, so we're here. We have the mole fractions, and now we want to calculate the partial pressures. So all we do, very easy, we multiply these mole fractions by the total pressure of all the gases in the container. So we're going to multiply this by 20. We're going to multiply this by 20. We're going to multiply this by 20 to find out what the individual pressure of each of these gases is in the container. And 40 divided by 11 times 20 is it's going to be 7.3. Here also it'll be 7.3. And then here it's going to be 5.4. All right. So Dalton's law of partial pressures, it's pretty simple. I don't think you'll ever get a question this easy, to be honest. But this is, now that you understand the concept, I'm going to go ahead in the next video. I'm going to show a practical example of when we'd use Dalton's law of partial pressures to find out some information. So go ahead and move on to the next video. Dalton's law of partial pressures is as simple as that.